of Mechanical Engineering, Parul University, and we'll enjoy the session. Okay, let's
Yeah,
start.
definitely. Thank you. So, Ronak, are you going to share some brief introduction, or shall I start and?
Yes, I'm going for a brief introduction about you, sir.
So, Ronak, are you going to share some brief introduction, or shall I
Yes.
start?
I'm
Yes,
going to
yes,
share
I'm
your
going
brief
to for a brief
introduction.
introduction about you, sir. So, Ronak, are you going to share some brief introduction, or shall I
Yes.
start?
I'm going to
Yes,
share
I'm
your
going
brief
to for a
introduction.
brief introduction.
Jiten bhai, is it live now?
Yes, yes.
Okay, fine. So, good afternoon, everyone. Uh, Welcome to the Mr. Chintan sir, Chintan Hingu sir, for the webinar on basics of pressure vessels and its design. So, Mr. Chintan sir is working with L&T Heavy Engineering as manager in design department. He has work experience of total 11 years and worked in L&T and Bechtel companies. He has experience of static equipments in design and detail engineering of oil and gas industry. He has hands-on experience of stress analysis. Moreover, he has extensive experience of equipment fabrication, testing, internal installation, and troubleshooting. If we look towards the education wise, then Mr. Chintan sir has pursued his B Mechanical with first rank from GEC Daod in 2010, in 2008, and he has pursued his master degree with CARECAM from SVNIT in 2010 with third rank. So it is our great pleasure to have Mr. Chintan sir as expert for today's webinar. So Chintan sir, over to you.
Yeah, First of all, I would like to thanks to Snehal sir, who was my colleague, who was my classmate in SVNIT, and as well as Ronak for coordination of this webinar. And of course, it is my pleasure to be with you, especially young engineers who will see the journey of pressure vessel and its design in basic terms in coming 1 year and in coming 1 hour. So I think my screen is visible to everyone.
Yes, sir. Your screen is visible.
Okay, fine. So I will start in. So as you see, that's what is the first impression or what is the first idea will come when we heard pressure vessel. So everybody has one understanding or one imagination that any closed chamber, when we say vessel, so it will be come as a closed chamber having completely bounded surface, having cylindrical shell or distant or some flathead, which will be the basically closed chamber and having some pressure, so that there would be some fluid or there would be some liquid inside the vessel under certain pressure, under certain temperature. So it is called as a pressure vessel. So any pressure vessel is having certain internal design pressure, internal design temperature, and having cylindrical wall, and subsequently it will be closed by distant. So this is the one typical photograph of pressure vessel. So pressure vessel design or pressure vessel fabrication testing is done based on the formula, based on the rules given in ASME boiler pressure vessel code. So what is ASME? Basically ASME is the American Society of Mechanical Engineers, which is the written guideline or which is the written rules for construction of pressure vessel. It entirely listed design formula, design rules, fabrication aspect, testing, NDT, welding. Everything is written in ASME boiler pressure vessel code. And we can see the pressure vessel in mainly chemical refinery, then petrochemical complex, likewise. So mostly process reactor, distillation column, separator, and storage tank, heat exchangers are common example of pressure vessel. So going to the pressure vessel design. So today's the agenda would be like this. First of all, I will cover pressure vessel design codes, then vessel geometry and construction, then some brief on strength of material on which the pressure vessel design is carried out, then vessel specifications, which various type of materials are required for construction of pressure vessel, then subsequent pressure vessel design rules as per the ASME code, and finally some brief idea or some brief hint on fabrication, inspection and testing. So this basically all these bullet points are taken care in ASME boiler pressure vessel code. So we will start or we will cover one by one. So now, as I have shared that ASME boiler pressure vessel code, which is basically written by American Society of Mechanical Engineers, widely it is the basically team comprises of so many members who has written respective chapter like design, inspection, testing, NDT, welding. So the team comprises of all the mechanical engineers and they have written certain guidelines, certain rules. So this is the one elaborative section wise detail you can see on my screen. There are total 12 sections written by ASME members. So first section, section 1, if you see, this is for the power boiler construction. Section 2 is mainly giving the detail of materials like it is carbon steel, low alloy steel, stainless steel. Section 3 talks about nuclear power plant components. Section 4 is for heating boiler construction. Section 5 is for non-destructive examination. For any pressure vessel, whenever you are doing welding, so subsequently some NDT is involved, whether it is radiography, whether it is ultrasonic testing or dye penetrant test. So this all the written rules or guidelines are given in section 5, which is basically for the non-destructive examination. Forward, section 6 is the recommendation rules for operating of heating boilers. Likewise, section 7 is also for the care of power boiler. Now it is our main heart. If you see section 8 is mainly for the pressure vessel construction. Section 8 is further splitted in 3 divisions. In total 3 numbers of division. Division 1, which is the basic rules, basic terminology and basic formula. Section 8 division 2, which is the basically alternative rules built after division 1, which is the more from analytical side, more stress analysis side. Section 8 division 3, it is again alternative rules but for high pressure vessel construction. Sometimes you can see that vessel thickness is 20 mm. You can see cylindrical wall thickness 20 mm. And we have fabricated 120, 150, 180 also. So apart from one thickness, there would be high pressure. And for that, ASME has given the special rules so that there should be safe operation, or in either terms, the pressure vessel must be safe enough in the prescribed condition, prescribed pressure, temperature like that. So our industry like petrochemical, chemical refinery, then other fertilizer refinery mainly requires division 1, division 2. Section 9 is more or less about welding and brazing qualification. I think that it has been covered by my colleague Kiran also. And coming to the another section which is related to fiber reinforced plastic vessel, not widely used in the steel industry, and section 11 and 12 is related to the nuclear and transportation tank. So our main focus in this webinar is on section 8 division 1, section 2, which is the basically material guidelines, material rules. As I have seen that fiber reinforced plastic is not mainly used in the steel industry. It is used for the bioreactor. So now what is the advantage of designing as per code? We see that so we will you will learn basic of pressure vessel in your college time or in your subsequent semester. But the what about the principle or about the fundamental rules, what advantage you will get by designing as per code. So first, that you will be having consistent formula, you will be having consistent practice as per for the design of pressure vessel, and of course the rules or law is same. So anybody is designing as per the ASME section at division 1 at India or at US, so the concept will remain same and there will be the uniformity. So of course this is the one of advantage, and everything is clearly written in code, so there is no ambiguity for the designer whether I have to select this or that. So that ambiguity will be eliminated by using this code. And of course, there is safety margins available in designing of vessel by using this ASME code. So there is no need to worry on that safety part. If you automatically follow the ASME code or ASME section 8 division 1 division 2 rules, so your pressure vessel for the prescribed condition is safe, provided you have kept all the margin or you have kept all the conditions in consideration when you design. And of course, since this is the uniform or this is the homogeneous code or homogeneous formula, consistent practice you have followed, so there would be some saving by optimization of the designing. Now coming to the section at division 1 and section at division 2. See, this is the mainly I will cover division 1, division 2 fundamental or brief. Then we will share or we will flow through the some basic concept on pressure vessel. So what is division 1 and what is division 2 will give you the further clarity or further chapter clear in your mind. So division 1, as I have mentioned, division 1 is basically for the general pressure vessel, which is having more factor of safety. So anybody can do design as per division 1 because there is certain formulas, certain rules are given. So you can use those formula from the division 1. You can find out the shell thickness, you can find out distance thickness, and you can design your pressure vessel or fabricate your pressure vessel accordingly. Now coming to division 2. Division 2 is respectively or comparatively iterative analysis, and it requires more inspection. If you go with division 1, there are less NDT or less material requirement exists. But when you go to division 2, it requires further iterative analysis or further FEA, which will be the very precise result in terms of thickness, in terms of dimensions. But at the same time, you will have lower safety factor. But at the same time, you are ensuring your pressure vessel integrity by using stringent NDT or stringent rules. Of course, you will get some benefit in terms of costing of the vessel when it is higher pressure. But if you see global level, division 2 manufacturer or division 2 fabrication is comparatively very tricky and difficult from division 1. So everybody nowadays is using division 1 70 to 80%, whereas division 2, when there is higher pressure vessel, heavy wall thickness, division 2 will be used. As per code, both the division 1, division 2 are acceptable, but you cannot mix. If you use division 1 formula and division 2 some allowable stress, so it is not possible or it is not permitted by code. If you use division 2 formula and division 1 allowable stress, so it would be some lenient case. So the same can be allowed based on case to case, but over and above, it cannot be mixed. Formula of division 1 and division 2 in your same pressure vessel cannot be mixed. If you are using division 1, then ASME section at division 1 shall be used for entire pressure vessel design, fabrication, welding, NDT and testing. And if you are using division 2, then entire philosophy should be used of division 2. Now vessels specifically excluded. So some lower or some without pressure or like having simply storage tank which are having pressure or water less than 2 MPa, less than 99 degrees Celsius, can be assumed to be excluded from the division 1. So these are the example where ASME section at division 1 cannot be used, or you can use your basic principle theory or basic concepts to determine dimensions. Now, if you use ASME section at division 1 and division 2 and it is code stem job, then you have to give nameplate to the pressure vessel. So that nameplate, or which is the basically identification of that pressure vessel, would be look like this. You can see this is the U. So that U is says that this vessel is code stamped or certified as per ASME section 8 division 1, and this will be given by your ASME authorized inspector. So that ASME has further dedicated authorized inspector to your works. So your authorized inspector will examine your design, will examine your welding, will scrutinize your all the entity related documents like radiography, ultrasonic, dye penetrant test. So everything will be scrutinized, examined by ASME authorized inspector, and then finally you will get certification or you will get code stamp nameplate. So it will be look like this, which is having name of manufacturer, pressure as well as temperature, minimum design metal temperature, manufacturer serial number or project number, and year built of that pressure vessel. So it will be typical code stamp nameplate. Of course, there are other codes as well exist in our industry, like ASME B16.5, which is the pressure vessel flange and flange fittings. Then B16.9, B16.47 for larger diameter steel flange. And of course, if there is heat exchanger, then additionally TEMA, which is the basically the guideline published by Tubular Exchanger Manufacturer Association, needs to be followed. Now, anybody or any engineer is designing the pressure vessel shall use latest edition or latest addenda of the code. Latest edition needs to be used in order to consistency in the formula, because ASME section at division 1, division 2 or entire ASME codes are getting updated or getting revised every 2 years, every 3 years, and it will be put into the practice subsequently. So anybody is using or anybody is designing pressure vessel shall use latest edition. Now pressure vessel design, vessel geometry. So we have covered what is the pressure vessel and how it will be designed, or what ASME section at division 1, division 2 gives you. So now vessel geometry. Mainly vessel geometry is spherical, cylindrical shell, and having certain thicknesses to be given. So it is basically the cylindrical shell having inside uniform pressure or liquid under certain temperature, certain pressure. So you can see the pressure vessel shape. This is the shell and this is the distant. Why distant is required? Distant is required to close the pressure vessel chamber. If you will not provide the distant, then it cannot be qualified as a pressure vessel because it is not the closed chamber. So scale of pressure vessel would be like this: 2:1, 3:1, 4:1. It is depend on the process parameter. If your process required that your distance or your shell is required 10-meter length, then you have to give 10-meter length. So this is the length of pressure vessel. This one is the length of pressure vessel, and it is closed by the distant. Vessel orientation. If we talk about the vessel orientation, it can be vertical as well as it can be horizontal. Horizontal vessel will be used when there is you can say that there is ample space available in the plant, so that horizontal vessel can be used. Where there is issue of pressure vessel space, or there is no sufficient space in the plant, then vertical vessel will be used, or your vessel will be mounted as a vertical. So it is basically the process as well as plant side requirement. Now, if you see closer, as I have shared that pressure vessel needs to be closed by distant. It may be hemispherical. You can see these three types of distant, which are basically the closure of the pressure vessel. So first is hemispherical. You can see this is the completely half circle. So these are the advantage of that hemispherical vessel, hemispherical distant. It is good for high pressure. Why? Because there is no discontinuity, there is uniform radius. So you will get lesser thickness when your pressure is very high. Second, high internal volume. You can see that there is also ample space available. So you will get internal volume high compared to other two distant. But it is most expensive. This fabrication process to make this hemispherical distant is comparatively difficult or tricky from another two distant. And by the formula of code, hemispherical distant will be having half thickness compared to the shell. So your thickness would be less, but at the same time, fabrication would be difficult or fabrication would be challenging for that hemispherical vessel. Another two distant, another two closer is ellipsoidal, which is simply 2:1. This phase is 2 times to this phase. So this is the 2:1 ellipsoidal head, which are the more commonly used in the pressure vessel. It is cheaper than hemispherical in terms of manufacturing, but you will get less internal volume. You can see that the volume is less compared to the hemispherical area, hemispherical head. Depth is almost half. As I see that 2:1, this dimension is 2 times, this dimension is 1 time. So of course depth will be half. And this thickness is same as shell, and it is mostly used when there is pressure greater than 15 bar. It is commonly thumb rule. And another distant, which is the torus spherical, it is part of torus having some different crown radius and knuckle radius. It is similar to elliptical but cheaper to fabricate. So all these three combination you can utilize in your design based on the fabrication aspect, based on the optimization aspect, and based on your costing aspect. So it should not happen that your design is very good or your design is fantastic, but at the same time fabrication is not feasible or manufacturing is not user friendly. So this design will not work or it will not be no longer work. So any designer or any design engineer should provide solution like user friendly, manufacturing friendly. Then your design would be successful. Now this is the basic terminology in pressure vessel design. This is the tangent length. When you connect shell with distant, you will do welding of distant and pressure vessel shell. So that way, one tangent length will be one tangent length will be there, and two weld line, which will be the connection of the pressure vessel shell and distant. So this is the basic terminology to be used during design of vessel, including head. Now going to some brief on the welded joints. Now pressure vessel can be designed, but it would be joined by terms of by using weld category or by using the weld joint. So you can see that there are different welds you can use based on your application, based on the rules permitted by ASME boiler pressure vessel code. When your vessel is having higher pressure, higher thickness, then these two types of butt weld joint. You can see butt weld joint means two subsequent or two shell layer will be kept together and having same level in same plane, and further welding would be done. So this is the butt weld, but it is single sided butt weld. And this is the double butt weld. You can see that double butt weld, you will be welding from both the sides. So that's why it is called as a double welded butt weld. So this is weld joint design mainly basically mainly depend on your pressure as well as temperature. When your temperature is very high, like you can imagine, we have designed or we have fabricated till 570, 600, even more than 650 degrees Celsius. So that way you have to use butt weld. You cannot use like this single fillet lap weld, because that single fillet lap weld cannot sustain that pressure or can that temperature. At that temperature or pressure, it will happen that this will try to open up and your vessel integrity or vessel would not be safe under the conditions. So this is the single fillet lap weld. When your pressure vessel is having very less pressure, less temperature and is not critical, then you can use single fillet lap weld, because there is only fillet weld at one side. And if you want more strength, then you can weld both the sides, as well as inner as well as outer. And fifth one is double fillet corner joint. This is the mainly case where you want to attach any structure component. So this is the basic weld joint we can use in the pressure vessel. Now if you see that pressure vessel can be closed by head distant, what we have seen three cases: hemispherical head, ellipsoidal head and toruspherical head. One another category is introduced by code like gasketed joint. When your pressure vessel needs to be opened or needs to be needs allowed to open for any maintenance purpose or for installation purpose, then you will use or you will construct in the segment. So if you will give this type of bolted joint, then your pressure vessel will be dismantled, or you can install any internals or any accessories, or you can have maintenance access for pressure vessel. So you can see that full face gasket. So whenever you are using flange, this is called as a flange to be used in the pressure vessel. So there is one gasket, because at the same time it should be leak free. If it is getting leak, then your again integrity, your vessel is not safe, your vessel is not under the safety. So you have to use or you have to apply suitable gasket over here, so there would not be any leakage criteria or leakage concern. So this is the full face gasket. You can see gasket placed on entire surface of the flange. Second case, if you see in figure B, there is the only gasket at that area only. There is no gasket at this junction, but your gasket material would be sufficient or would be adequate to sustain the entire load coming onto the zone. And there are certain another type of gasket also available or also acceptable by ASME code. It is like you can see when your pressure is high or you have leakage concern. So you can use like this also. So what will happen? Your liquid will not go or liquid will not bypass. So ultimately your pressure vessel would be leak free. So these are the different type of gasketed joints. Now if you see pressure vessel typical construction, we have seen already, or we have covered shell as well as distant. Now one more category or one more component is added. Whenever you want any inlet or outlet, you need nozzles, which is opening. You cannot imagine with pressure vessel without nozzles, because nozzles is required for particular service. If you give any input or if you give any liquid inlet to your pressure vessel, then what will you do? So you require nozzles. It is mounted on shell or it is mounted on the head. Of course, in order to maintain or in order to check the temperature, we require some instrument nozzle as well, which will measure pressure, temperature or liquid level inside the vessel. So there are some instrument nozzles also required on your pressure vessel. Then coming to the when if you want to, or if you carry some inspection activities inside your pressure vessel, so you have to provide some manways also. Manways is also nozzle, is type of nozzle, but having larger size to allow access inside the pressure vessel. It's generally 24 inch to 30-inch sizes. So this is the nozzle. Many number of nozzles would be more, so then cost would be more. So this is the simple criteria. Now, if you give cutout or give some openings to pressure vessels, so you are compromising strength of pressure vessel, or you are reducing the strength of that pressure vessel. So you have to provide some reinforcing pad, so that your cutout area or whatever you have cut the pressure vessel, it will be compensated, right? So here you can see that one reinforcing pad is provided to the external side of vessel shell, which will basically having function to strengthen the pressure vessel at this junction. Whenever you are giving cutout or whenever you are making cutout, this area will be lost. So equivalent area needs to be provided either by reinforcing pad or making this nozzle neck wider or nozzle neck thicker. So all those reinforcing pad calculations, vessel wall opening are given in the boiler pressure vessel code. Now it is swag vessel. Such type of vessel is also allowed. It is also acceptable based on your process. Here is the cone. You can see this is the frustum cone, and this design rules are comparatively different than the shell, and it requires some more iterative analysis because you are changing the shape of pressure vessel. Rest all the construction are same. Now coming to the vessel support. Any pressure vessel is designed or fabricated, but you have to mount on site as well, right? Like you can imagine our body. For our body, legs are our support. Our legs are support. So like that, any vessel or any pressure vessel, heat exchanger, reactor should have support or should have cut or saddle. Now, if you see horizontals, so there are two saddles on which your vessel is mounted. So it is called as a saddle. And if you see the pressure vessel mounted vertically, so it is having skirt and it is the base ring. So this entire vessel support needs to be designed or needs to be calculated for the specified loading. And this pressure vessel will be mounted on the side on foundation. You can see that in figure A, there is some foundation and there is one bearing plate on which your vessel or your skirt would be mounted and entire vessel will be rested. Now, can you imagine that tall vertical vessel are often supported using the skirt rather than legs? Can you think that? Because the reason is that if you see leg, so that leg is only 4 numbers or 3 numbers depending on your the application. But when you use skirt, then it will be entirely covered. So your tall vertical vessel will be subjected to very high load or very high compressive load, dead load. So that's why you require full skirt. So that full skirt would be the 360-degree cylindrical shell. Now coming to the vessel supports to the intermediate. Such type of construction is also acceptable. So you can imagine or you can visualize if your vessel support is mounted at this junction, then this will be having some pressure or some storage liquid or some dead weight. So there would be in the tension nature. Cylindrical shell would be in the tensile force nature. When there is upper portion would be in the compressive zone because dead weight is acting downside. So it will cause some compression inside the wall and it will cause some tension force inside the wall. So it depends on your process fluid, it depends on your pressure, temperature, and it depends on your application. Now coming to the jacketed vessels. So there are certain another categories also acceptable. If you want jackets, so this is the main pressure vessel. This boundary is for the main pressure vessel, and it is the outer vessel or it is the outer boundary which is called as a jacket. You can imagine we have wear the jacket and first layer inside our shirt and second layer is the jacket. So jacket is having more area for the fluid rotation and will give you the desired heat transfer area as well. So this kind of jacketed vessel is also applicable, acceptable, and this can be manufactured. But it requires certain different rules or need some more attention towards the design. We have talked many things on the pressure vessel. This is the distant, this is the shell, this is the bottom distant, this is the nozzle. So you can visualize this 3D or you can see this 3D where there are different component of vessel is given. But building only pressure vessel is not enough. So there would be some internals. There would be some internal components which required for the process. So these are the mainly like inlet basket, then this is the distillation tray, then this is the packing support, distributor grid, heating coil. So these are the mainly for the function. If these components are not there, then your pressure vessel is no longer having function. So in order to get desired function, these internals are the key component of your vessel. It depends again on your process, what flow rate you require, what pressure you require, what pressure drop you require, what is your temperature, what is your outcome. So this is designed for the process side. You can see the nozzle here as well. Whatever we have seen, this nozzle would be look like this. There is one inlet over here, and you can see that gas will be flowing towards upside and outlet through liquid through outlet nozzle will be collected at the bottom side. So this is the one typical function or typical example of pressure vessel along with internal. Now coming to the strength of material aspect, this is the everything is related to the strength. Any pressure vessel design is attaching with or is mainly concentrated to the stress and strain formula. Stress is mainly force divided by area. So area is your original cross section under the tensile force. So you can imagine that there is tensile force. So your stress would be force upon cross sectional area. And again strain. Of course, this is the very preliminary or very fundamental theory which is the required for any pressure vessel design. So again strain is the distortion per unit length. So this basic concept is required for the pressure vessel design. I am not going into depth as you will learn or you have many of you have learned about stress and strain concept in your mechanical first year. So this is the same concept, this is the same theory which we use in the pressure vessel design. Again, this is the stress and strain curve. It is also, you are also familiar with this. So your stress is directly proportional to strain up to the elastic limit, then your plastic limit will start, and after certain stage, your maximum load will be reached, and ultimately your failure would be arrived. So our pressure vessel design is also based on the same concept, same principle. Here is the creep. Creep is the totally different, or perhaps you have not go through this creep terminology. Creep is basically the failure under the increased load over the time period. Now, here time period is also attached or time period is also included. So now your strain delta L upon L, change in length or change in the dimension upon the original dimension would be increased or would be modified over the time period. You can imagine your temperature or your pressure vessel is working for 10 years. So when you put into the application at first year, it will be having very good performance, very good function. But over the period, you can imagine that after 10 years, your process or your output would be different than it is at first year. So it is due to the creep, and creep is the basically metallurgical phenomena, and it is mainly dealt with the increased load over the time period. Now here is the some stresses or some principal theory for which for which we need to take into the consideration while we are doing pressure vessel design. So first is principal stresses theory and maximum stresses theory. Both are little bit different and having results slightly different. So first principal stress theory is used in division 1. It is again the failure theory which gives the principal stresses and its criteria. When it exceeds the value, allowable value, then your failure would be caused. So as per the theory or as per the rules, you have to find out your thickness such that your induced stress or your stresses in your vessel is less than your allowable limit. Now there are different failure of material and principal theory is written or is based on the our principal theory based on your our concepts. So that is maximum principal stress theory, maximum shear stress theory, maximum strength theory. So our ASME section at division 1 is based upon the maximum principal stress theory, in which your induced stress would be comparatively higher than maximum shear stress theory. This both the theories are different and are used in ASME section at division 1 and division 2. So this mode, if you use with maximum shear stress theory, your induced stress in component would be little bit less, or you will get some higher limit in that case. Now coming to the loads causing the stress on pressure vessel walls. So right till now we have seen that what are the basic concepts of pressure vessel, basic components of pressure vessel, how distant will be attached. So now coming to the core concept or core design, like any pressure vessel is having some internal pressure. Of course, there would be some external pressure as well. When your internal pressure is zero, then your atmospheric pressure would be acting and there would be some negative pressure inside the chamber. So your vessel would be sufficient or would be adequate to sustain that load as well. So first is internal and external pressure. Second is dead weight of vessel. And third like weight of internals, then wind and snow. So all these loadings you need to consider when you are designing any pressure vessel wall. You can see the one example. Your vessel is mounted and your wind is acting like this. So there would be some bending moment, right? So you have to take care of this bending moment, wind force in your calculation such that whenever there is storm or then whenever there is seismic, your vessel withstand that force. So this all these aspects are given in the standard reference. Now coming to the theory, this is the simple hoof stress and longitudinal stress. And again, it is the principal design of pressure vessel. So if you see that horizontal section, which is nothing but like this, so sigma L will be term like PD by 4T. You can derive this formula or derive this equation by using cross-sectional upon resisting area method. And if you see hoof stress, it will be PD by 2T. So you can imagine that sigma H is PD by 2T and sigma L is PD by 4T. So comparatively, longitudinal stress is having PD by 4T, so that your governing stresses would be counted while you are designing. Now vessel specification. So what you require or what you need for the pressure vessel design. So you need vessel size, like inside dimension of vessel. You need length. You need vessel orientation. vessel elevation, and of course its design temperature, its design pressure, which are the very key parameter. If you don't have design pressure, design temperature, then you cannot do any vessel design. And if there is any vessel internals, you require some information of that. And most important things, your pressure vessel material, which material you are using for pressure vessel fabrication or pressure vessel design is the main thing, because your allowable stress or your stresses would be based upon that. If you are using carbon steel material, if you are using low alloy steel, your allowable stress would be different, then your thickness would be different. So this entire thing needs to be considered or kept in mind when you are doing any design. And of course, corrosion allowance. As I have shared, at first year, your vessel would be having good performance, good function. But after 10 years, there would be some corrosion allowance, there would be some erosion, due to which your wall thickness would be reduced. So that corrosion allowance you have to add when you are designing vessel at a first time. So this is the pressure vessel specification, or either way we can say this is the design loading conditions. So this is the mainly related to design pressure. If you see on the plant side, normal operating pressure is basically pressure vessel which will be suspected to have that operating pressure. Maximum operating pressure. If you have shutdown or if you have some emergency startup shutdown condition, then what would be your operating pressure? So this pressure would be derived during your process design. And third, which is very critical, very important, design pressure. Design pressure is having certain margin over to operating pressure, so that if you have some maximum operating pressure like 10 bar, so it will be achieved or it will be reached to the operating pressure, then your design pressure set to the maximum operating pressure would be failed. So you have to use some margin of safety on the design pressure, like say 10%. If your maximum operating pressure is 10 bar, then at least 11 bar or more than 11 bar you have to set as a design pressure. Code is not saying that how much allowance or how much safety margin you have to keep, but it is the process guideline or it is the plant guideline for safe operation. Again, we have already shared the design for vacuum. Design for vacuum would be look like this. If you have not used vacuum design in your pressure vessel, then you can see that there is some internal force which will pull the vessel inside and it will collapse. You can see one typical example of the pressure vessel failure under the vacuum. Entire vessel would have some pull force and it causes failure. So similar concept is also applicable or applies to the design temperature. Your operating temperature is, let's say, 400 degrees Celsius. So you have to use certain margin, safety margin, to set the design temperature, like 50 degree Fahrenheit. So your 450 degree Fahrenheit operating temperature would be 500 degree Fahrenheit temperature for your designing the vessel. And each pressure vessel design would be designed on design condition only. You cannot use or you cannot design your pressure vessel on the operating condition. You have to use design condition, which is the very stringent, which is the very more conservative condition, which is taken care of all the transient conditions, offset, auto refrigeration, climatic conditions, or any emergency shutdown conditions. So any designer or any pressure vessel design engineer who is designing the vessel should use design pressure, design temperature. Though you have sufficient margin in operating pressure, you cannot use operating pressure, operating temperature. You have to use design pressure, design temperature. Now here is the design temperature consideration which you have to use for the safety margin, and further it is some guidelines given in ASME section 8 division 2 on which you have to use design temperature consideration. Here is the one example. Here is the 120 psi is given here. So you have to use as a 25 psi as the safety margin, and your pressure design pressure would be 145. So this 25 psi is the safety margin with you. 120 is your operating pressure of this pump, and 25 is your margin. At the same time, design temperature, it is 340 Fahrenheit, and it is the additional safety margin. So your entire pressure vessel would be designed on 145 psig and 390 Fahrenheit. Here is also similar. It is kind of heat exchanger. Your process fluid would be flow like this, and it will be coming look like this. So here is the inlet, and here is the outlet. So both the pressure vessel chamber is having different conditions. Now material of construction. We have covered pressure vessel basic, pressure vessel material, pressure vessel design conditions, loading conditions. Now crucial thing, which kind of material you are using as a construction of vessel. Suppose when you are selecting or when you are when you choose the material, when you select your material, whether it is carbon steel, alloy steel, stainless steel, non-ferrous, so there are so many varieties are available, so many varieties exist in the market. So which kind of material will be suited to your application, that to be selected by you when you are using process design. And of course, when you are doing or when you are selecting this thing, you have to of course take into mind that it should be available in market, it should be manufacturable, and it should be available in standard size as well, like plate, section, tube. And of course, over and above, you can optimize your cost by having certain optimization in your material as well. So main common material used in pressure vessel fabrication, pressure vessel design is carbon steel, then low alloy steel, then stainless steel, and nickel alloys. Carbon steel is corroded, having tendency of corrosion. Same way, low alloy steel is having tendency, but it is having corrosion resistance compared to the carbon steel and filled carbon steel. Stainless steel is the comparatively costlier material, carbon steel and low alloy steel, but it is having very good resistance to corrosion. So it may happen that with stainless steel column, stainless steel pressure vessel, you should have corrosion allowance as a 0. And nickel alloys, when your process or when there is a critical chemistry or some exhaustive chemical composition should happen or should occur in your vessel boundary, vessel chamber, then you require some rich chemistry. So nickel alloys would be used. So these are the commonly used material in vessels. Now if you see that this is the one relative cost example, and if you use carbon steel, your costing of vessel would be less compared to the stainless steel and nickel alloys. But at the same time, you would have different allowable stress. If you use carbon steel material, you have 12.9 psi, 12.9 ksi, sorry, 12.9 ksi. And if you use austenitic stainless steel 304 grade, maximum allowable stress would be 20 ksi. So each and every different material has different allowable stresses. Now corrosion allowance. Corrosion allowance is given 1.5 to 5 mm based on your process. So it is very key parameter while defining the thickness. Now pressure vessel design rules. So it is basically the formula given by code. So if you want to define the thickness or define the wall thickness, you have to use certain formulas given by boiler pressure vessel code, ASME section 8 division 1 division 2. So minimum wall thickness is required 1.5 mm. Though your vessel is having certain pressure and your thickness is 0.75 mm, you cannot use 0.75 mm or 1 mm. At least you require 1.5 mm. And if your corrosion allowance is 3 mm, then this thickness will be further increased to 4.5 mm. So this is the very basic concept or basic theory. Which formula you will use to derive the thickness is given by ASME section 8 division 1 division 2. So here is the formula you can see on the screen. So here is the formulas of hoof stress and longitudinal stress. So here is the pressure, internal pressure, and here is the inside diameter. And S is your maximum allowable stress at that temperature. So you can see that internal pressure effect is taken, inside diameter is taken, allowable stress at that design temperature you have to take. So again, temperature effect is also considered in terms of allowable stress. And this is the very, very interesting as well as significant chapter in our pressure vessel design, which is the joint efficiency of weld joint. So if you using radiography is basically the X-ray examination of pressure vessel. So you will get joint efficiency as a 1. And if you are using radiography for entire length of your vessel, then you will get joint efficiency as a 1.0, means 100%. So your thickness would be at 100% efficiency. Now, if you have some limitation in radiography, limitation in X-ray, and if you are using spot radiography, which will keep or which will take only 2 spot per seam or per weld, then this factor will be reduced to 0.85. So ultimately your thickness would be higher. So you can imagine that whenever you are reducing the extent of non-destructive examination, your thickness would be higher or your thickness would be increased. So similar, the case would be the for longitudinal stress. So with this, you have to use higher thickness from these two formula for your vessel. Here is the maximum allowable stress temperature. You can see that maximum temperature 900 degree Fahrenheit, and here is the maximum allowable stress. You can see that at 100 degree Fahrenheit, 12.9 ksi is your allowable stress. Your temperature would be higher, your allowable stress would be lower. Right. So this is the one example or this is the one case where you can use allowable stress for thickness calculations. Now, if you see carbon steel and your temperature is 900 Fahrenheit, your allowable stress is nearly 5.9 ksi. But in the same time, if you use stainless steel material, your allowable stress would be 11.5 ksi. So you can further reduce the thickness, but at the same time, costing will be higher in stainless steel material. So optimization has to be done during the process as well as mechanical design. Here, this entire thing is taken from ASME Section 8 Division 1 and ASME Section 2 Part D, which gives you material properties. Now, this is a very interesting chapter in pressure vessel design, like welded joint categories. Welded joint categories is defined as this is the circumferential joint. Circumferential joint, this one. Category A joint is the longitudinal joint. This is for any cylindrical shell, and this is the circumferential shell, circumferential weld joint, which is category B. So, code, boiler pressure vessel code has separately given category, and based on that category, you have to find out required NDT, required thicknesses, and required testing. Category A is mainly longitudinal seam. Category B is mainly circumferential seam. So category A, the thickness would be double than this category B. Category C is like a flange to pipe joint. And category D is the corner joint of nozzle to shell junction. So this is the figure from ASME boiler pressure vessel code. Based on the different category, it is full, sport, and none. As I have shared, if you use full radiography, then you will get factor 1, joint efficiency factor 1. And if you use spot radiography, 0.85 you have to use. And if you are using, and if you are not doing any radiography, any NDT examination, then your efficiency would be 0.7. So you can imagine or you can calculate that your thickness would be always higher. So again, this is the joint description, this is the joint category, and This is the extent of radiography examination. And of course, that's the closures like distant would be having this formula. If you want to use the distant and you want to calculate the thickness, this formula should be used. Now this is a one of example. Due to the limitation of time, we will not see, but you can. I have shared my PPT with Ronak, so you can see or you can try from your side. So it is the basically formula, and you will find the calculation or you will find certain thickness like this. Now what? This is the manual calculations, but in our industry or in our day-to-day work, we cannot do manual calculations. So of course, some softwares to be used, some standard available vessel design softwares needs to be used, which are very reliable and which are the tested. So one software is like Compress, one second is the pressure vessel suit, and third is the PV light. So these are the pressure vessel softwares which we can use for any pressure vessel design. The same formulas will be used by software as well, and the allowable stress as per the ASME section 2 part D based on your division 1 division 2 applications. And fabrication inspection testing aspect, fabrication would be look like this. If you want to use or if you want to fabricate any shell, so it will be having rolling process. You can see the roller, and this is the your ID, vessel ID. So this will be manufactured by rolling process, and after shell is rolled in segments, then you can weld succinct circumferential joint. And when your pressure vessel is ready, you have to weld distant on the both the sides. And after that, you have to carry out non-destructive examination like radiography, ultrasonic, or dye penetrant based on your design or based on your applications. And afterward, you have to carry out water testing or pressure test on that vessel. And here is I have covered one critical aspect of vessel. As you have seen that so many process like fabrication, welding is involved in pressure vessel fabrication, pressure vessel manufacturing. There are some internal stresses or there are some residual stresses would be arise during your fabrication. So that to be removed in order to maintain your toughness or hardness of the material. So in order to regain those mechanical properties, you have to carry out heat treatment. So heat treatment is very, very essential aspect in pressure vessel design, and it shall be carried out as per the guideline. So many material is having different requirement of PWST. If you are using carbon steel material, then you have to carry out post weld heat treatment. And if you are using stainless steel material, then post weld heat treatment is not required because there would not be any impact of residual stress for the stainless steel material compared to the carbon steel. So these are the different concepts of post weld heat treatment. So over to that, we have covered general pressure vessel, how it is, what are the different types of component of pressure vessel, like nozzles, distant, cylindrical shell. Then we have seen uh, what are the different materials are involved in pressure vessel fabrication. What are the different rules, different formulas to determine wall thickness, how it is designed, and on which basis of strength of material it is written. So this all we have covered at utmost possible. So thank you.
Thank you very much, Chintan sir.
Yeah, thank you.
Thank you
So
very much, sir, for
yeah,
sharing the very important points related to the pressure vessels, its design, the failure criterias, and even importance of the SME codes. and its implementation in the pressure vessels. So I think it will be very much helpful to the students to understand the importance of ASME code in the industrial aspects and the basic design of the pressure vessel. So thank you very much, Chintan sir, for sharing your knowledge here with the students and all the faculty members. And even I would like to thank the management for providing us the this kind of opportunity to conduct such kind of webinars, and even the PU webinar team, Mr. Brijesh Acharya sir and Mr. Jiten Bhai, for continuous support in the conduction of such webinar. Thank you very much, sir.
Thank you all, and it was my indeed pleasure to be with you, especially young engineer to whom I can spoke to at least some preliminary level or some importance of code. So it is very essential nowadays to have update of ASME code. See, mainly the thing is that design we know, principal theories we know, fundamental we know, but over and above, industry demands uniformity or consistent design in every aspect. So this type of codes or this type of written rules are very essential parameters nowadays, and it must be known to everybody. So thanks again to give me this opportunity to share the presentation with all of you. Thank you. Thanks you.
Thank you, sir. Thank you.
So shall I log off or?
Yes, sir. Sure.
Okay.
Yeah.
Thank you. Thank you all.
Yeah. Thank you, sir. Jiten bhai, shall we end up now?